Hello, my name is Ashkbiz Danehkar. I am a research scientist at Eureka Scientific Incorporations, funded by my NASA EDAP grants, and I worked on the service-driven outflow with Sally O at University of Michigan and Will Gray. And I recently tried to extend my hydrodynamic simulation to AGN-driven outflow. This is the outline of my talks. I will talk about multiplication for AGN outflow simulation, galactic wind theory, and hydrodynamic simulation setups, and different wind modes, and photoionization calculation, and my future plan. And motivation for AGN outflow simulations. There is a work by Tumbasi in which he studied a sample of radio quiet AGN, and he derived outflow velocity and ionization parameter and column density, and he found a correlation between outflow velocity and ionization parameter. And there is also a work by Pounds and King, NGC 4051, and they fit warm absorber, different component of absorbing components, and as you see, there is a correlation between velocity and ionization parameter of different absorbing components. And also on the bottom right, you see the plots from Tumbasi 2015, in which he plotted momentum flux normalized to radiations against wind outflow velocity for inner winds and molecular outflow. And this different work suggested that there could be a single large-scale outflow and compact outflow related to large-scale outflow, as you see in this schematic view. Based on this correlation, we arrive at a schematic view of shock wind. You see different regions, adiabatics, shocked wind, two body cooling layer, and also shock fronts, and the formation of hot bubble. And on the right, we see a schematic view of multiphase energy derivatives outflow, and we see the formation of molecular gas clumps because of instability. So this density column could be related to those warm absorber which I previously showed. Four different regions of galactic wind defined by Weber in 1977. First is free expanding wind, then the hot bubble, and after that a formation of the shell, and which followed by ambient medium. And for larger scale galactic winds, there is a theoretical model developed by Chowley and Kellage in 1985, in which they study adiabatic winds. However, they didn't include radiative cooling functions, and this adiabatic wind has a trend which on temperature and density as a function of radius. By including cooling function, we see there is a departure from adiabatic winds, and this radiative coolings has a dependence, as you see, on metallicity. With higher metallicity, we have higher coolings. However, there is a difference between service-driven outflow and AGN-driven outflow. In a service-driven outflow, the wind typically is slow, and as the wind is became slower, it triggers star formation because of formation of cooling regions. And the ambient density, as you see, they are typically the same. And however, the service-driven outflow have lower ionizing luminosity, and they are typically in metal poor star-forming galaxy. However, in AGN-driven outflow, we have fast winds. As the wind became faster, it quenched star formation because of formation of high temperature. And in AGN-driven outflow, ionizing luminosity is higher, and when we are near supermassive black hole, they have considerable gravitational force. To simulate AGN and also star-driven outflow, I use a model which implemented in Flash, radiative and chemistry networks module Mayhem, and we have some input parameter: mass loading rate, wind terminal velocity, injection radius, and physical condition, ambient mediums, density and temperature. And we set the initial condition and boundary condition based on analytic solution. Other important parameter and input is ionizing SED, because we use it for photoheating rate, also photoionization rates. This photoheating rate and photoionization rates calculated using photoionization cross sections. And here you see the fluid equation which used for my hydrodynamic simulations, and which is coupled to radiative cooling function calculated using cooling efficiency, and photoheating function calculated using photoionization cross sections. And here you see an example of our hydrodynamic simulations. There is 3 different winds with 250, 500 and 1000s. And as you see, on the slower wind we have stronger radiative coolings which contribute to a departure from adiabatic flow. On right, I show the 2D simulations which show the formation of large scale bubble. And based on departure from adiabatic solutions, we define adiabatic bubble and catastrophic cooling bubble and catastrophic cooling without bubble. And here you see different wind regions which I classify based on temperature departure from wind from adiabatic temperature. And we have adiabatic pressure confined mode, in which the bubble is assaulted by high pressure of ambient medium, reducing wind velocity with increased radiative coolings. And here is a different plot. As you see, by increasing mass loading rate, we also increase radiative cooling. And in this plot you see different collective wind mode, energy derivatives mode, and momentum derivatives modes. Bottom left we have momentum conserving, and this is a schematic view of momentum derivatives and energy driven outflow. In energy derivatives outflow, the shock region are much wider and we don't have very strong coolings. However, in the momentum derivatives outflow, shock region are very narrow and rapidly cool. We don't have the formation of extended hot bubble. And I also did photoionization calculations. Here I show the schematic view how I implement photoionization calculation. I use density and temperature and ionization state calculated by cloudy, not or hydrodynamic simulations. And so this produce photoionizations plus collision ionization. And other thing is time dependence effects, which show its effect in non-equilibrium ionizations. When the time scale of collision ionizations, it is much larger than time scale of radiative coolings. For this is true for oxygen 6 and carbon 4 below 10 to the power of 6. In this plot I show the on top pure photoionization, and in middle I show collision ionization plus photoionization, and on bottom we see 3 non-equilibrium photoionization. Now other thing which I plan for future is including radiative transfer units, which will allow us to study radiation-driven winds. And here is a summary of my talks. Thank you for your attention, and if you have any questions, you can post in Slack and I will answer.